Hello, welcome to Can We Do That Some More, the series where we basically give ourselves an excuse to just do more maths based on the things we were looking at in the most recent Can We Do That video. Of course, that video was, for us, second order derivatives of parametric equations. So do have a look at that Can We Do That video if you haven't already. But if you have, today's video, of course, in this series, we look at just giving you an excuse to have more questions based on the stuff we were looking at before. It's just a chance for me to try maths, for you to try maths, for us all to just have fun while we're doing it. Before we do continue any further, though, I should warn you, like the Can We Do That series, this is stuff you don't need to be doing for the Maths A-Level or further Maths A-Level exam. We're just doing this maths because we want to do this maths, not because we need to know it for an exam or anything like that. Anyway, therefore, I should remind you, though, if you hopefully you did watch that last video, but if you didn't, a reminder that the equation for finding the second order derivative, d squared y over dx squared for parametric equations, is what you can see on the screen. We're going to be using that equation throughout this video, so if necessary, pause the video briefly to allow yourself time to write down that equation. I already have it on a bit of paper to the side of me because it's going to be useful. We've already done the proof of it, so we don't need to derive it manually every single time. That would defeat the point of doing what we're doing today to a certain extent. Right, okay. Here are the three main questions that we're doing today. So again, you're welcome to pause the video at this point and have a go at them yourself. But what is going to happen after this moment is I'm just going to be going through these three questions just because I want to. So there we go. I haven't done the questions already, so I don't know the answers. So apologies in advance if I'm making mistakes along the way. Do let me know in the comments. But I have at the very least checked that these questions do have solutions, so I'm not just going on a wild goose chase. Right then, question one. So we've got our two parametric equations or curves. I've suddenly realized, of course, in the previous slide, I'd pointed out that we've got a interval for our solutions that I had forgotten to copy over. Actually, let's double check that. Yes, it is 2 pi. So there you go. A very dodgy written pi there. But there you go. So let's go and find the coordinates of the maximum point. Of course, to do that, we're going to need to first find the first order derivative. So let's take x, differentiate that a couple of times. So therefore, cos would differentiate to minus sine. So it's minus 5 sine t. The minus 4 will disappear when we differentiate it. Y is equal to 2 sine t plus 7, and therefore dy over dt is going to be equal to 2 cos t. Again, the 7 differentiates to 0. So therefore dy over dx is equal to dy over dt, so 2 cos t, over minus 5 sine t. But to a certain extent, that denominator is kind of pointless. If we just want to find stationary points, dy dx is equal to 0, and then in reality, therefore, it's just the top that matters. And then solving that equation, that's such a simple equation solved between 0 and 2 pi. I'm just going to skip some steps, be a little cheaty, just because that's such a classic trig equation. I know the answers are pi over 2 and 3 pi over 2 if we're dealing with radians. Nice, so those are our two stationary points, but we need to find which one is the maximum. So we differentiate again, finding d squared x over dt squared. That will be minus 5 cos of t. And find d squared y over dt squared. And that would be minus 2 sine of t. That means we now have all the things we need to find d squared y over dx squared. So we can do that. So according to the formula, that means we'd have our d squared y over dt squared times by our dx over dt, which is minus 5 sine t. Terribly written there. Minus dy over dt, which is 2 cos t, times by d squared x over dt squared, which is minus 5 cos of t. And we're dividing all of that by, a terrible line there. You can tell I'm doing all these videos live. Mistakes will be made. Terrible handwriting will happen. But it's fine. So that's what, not squared, there you go. Or first mistake of the day, cubed. Dx over dt all cubed on the bottom is the formula. Brilliant. So all you've got to do now, I mean, you could admittedly choose, if you wanted to simplify the top. Because funny enough, for this one, it's going to become 10 sine squared t plus 10 cos squared t all over minus 5 sine t all cubed. So that's minus 125 sine cubed t. And the reason I bothered simplifying that is because, if I fit this in just above my camera, that, of course, you notice on the top, we've got sine squared plus cos squared happening. Or I should say sine squared t plus cos squared t happening. And we've got 10 lots of it, so that's just going to simplify to 10. So hooray, that trig identity comes in useful. You could even divide top and bottom by 5, actually, now looking at that as well. Wow. It just keeps on going on, doesn't it? So we've got minus 2. And then on the bottom, we've got 25 sine cubed t. So there we go. That's what d squared y over dx squared simplifies to. And so now I can plug in pi over 2 and 3 pi over 2 into that. So at t equals pi over 2, d squared y over dx squared is equal to, well, minus 2. We got pi over 2. Sine of pi over 2 is 1. 1 cubed is 1, so it's minus 2 over 25, which is less than 0, less than 0, which means it's a maximum. Oh my goodness, there we go, we found it already. That is the maximum point. Just to confirm though, at t equals 3 pi over 2, cramming it in at the bottom here, we can probably already guess what the answer is going to be. That's why I'm happy to do this. That would be, well, minus 1 all cubed is minus 1, so it's positive 2 over 25. Okay, so because that's greater than 0, therefore it's a minimum. Surprise, surprise, who saw that coming? However, worth pointing out, the question asks for the coordinates of the maximum point. So actually, t equals pi over 2 is just the value that creates the maximum. So I actually have to plug t equals pi over 2 back into the original equations to find that as coordinates. So cos of pi over 2 is 0, so therefore it's minus 4 is our x coordinate, and our y coordinate will be, well, sine of pi over 2 is 1, so it's 2 plus 7, which is 9. So the maximum point is minus 4, 9. There you go. I managed to cram the whole question on one screen, which looks horrendous to look at, but hey ho. We got our answer. Nice. Let's go on to the second question. Wow. So we've got these parametric curves here. But I tell you what, for this second question, first of all, I was just curious as part of checking whether there were solutions. As I said, I don't know what they are yet, but I did at least check that the solutions exist. I checked that there were stationary points on it. I looked at the graph, and the graph looks like this, which I think is quite cool. I always like looking at crazy graphs, and it once again shows the advantage of not just sticking to Cartesian equations that are of the that have y as the subject of the formula, because they're far more restrictive. You have weird, loopy thing happening, which wouldn't happen if you had a different. If you had just a traditional y equals graph. I then also went to the effort of, just out of curiosity, finding the Cartesian equation of this curve, and funny enough, it took a bit of effort, but it looks like this. And at first glance, it looks not too bad, but actually, when you look at it a bit more, you realise this shows why parametrics aren't just useful for situations where that third variable has a meaning. They're actually also useful sometimes just because it makes the question easier. If this Cartesian curve, if you wanted to differentiate twice, sure you could do it, but you'd have to do implicit differentiation as part of a quotient rule, as part of a chain rule. And that's just the first order derivative. If you're doing that with the second order derivative, it's going to have even more of that stuff, which would be a really big chore. You can do it, but I wouldn't want to. So actually, parametric equations are awesome here's the example of why. Because obviously, our parametric equations in this case are just polynomials, which are easy to deal with when it comes to differentiation. So part A, find the t-values of the stationary points. Okay, all I've got to do is differentiate. Well, I'm going to differentiate both of them, but technically you do actually only need to differentiate finally enough the x. So therefore dx dt is 10t minus 4. dy over dt, the one that actually matters, is 6t squared minus 10t minus 4. Of course, we set dy dx equal to 0. You could find dy dx yourself first, but in reality, if dy dx is equal to 0, I'm just going to say that immediately the top of the fraction, which would be the dy over dt, is equal to 0. Anyway, so you've just got to solve that quadratic equation. It is one that factorizes. I can see that, but I don't want to factorize it. I'm just going to use the quadratic formula. Amazing. So if you use the quadratic formula, you'll find that t equals 10 plus or minus square root of 10 squared minus 4 times 6 times minus 4 all over 2 times by 6, which is 12. And if you do that, you'll get t equals 2 and t equals minus a third. There you go. So there you go, much less brain power used there. So those are the t-values of stationary points. Nice, on to part B, which is determine the nature of the stationary point. So again, we need to find d squared y over dx squared. So we have our x, we can find dx over dt. I already did, but I forgot to copy it across. So therefore we got 10t minus 4. We can differentiate that again, not to get d squared y, to get d squared x over dt squared. That'll get us 10. We can differentiate the y equation twice. We already had this from before. And then we can also differentiate that again. And that's going to get us 12t minus 10. Lovely stuff. So therefore d squared y over dx squared is going to equal 12t minus 10 times by 10t minus 4. Take away dy over dt, which is that entire quadratic, times by just 10 actually, so I could put, can I cram it in there? Yeah, we can. Minus 10 lots of that quadratic. All divided by, oh goodness me, my straight lines are not very straight today. All divided by dx over dt all cubed, so that's 10t minus 4 all cubed. Okay, good stuff. Now, admittedly, the top of this fraction could simplify. I'm not going to bother just because I know we're just immediately going to be plugging a number in, and it's still going to be a quadratic. So we'll save a bit of time, but not tons and tons and tons of time. So therefore, let's go ahead and type those in with our t values. I mean, let's first write that down. So at t equals 2, because that was our first stationary point, we are going to plug that all in. So that being going to be 12, take away 10, which is 2, times by 6 minus 10 lots of, and that would be 6, take away 10, take away 4. All over plugging in t. Oh no, wait a minute. I've just completely mucked that up. I wasn't plugging in t equals 2. That's completely wrong. Let's go back. So actually plugging in t equals 2 is going to be 24 take away 10. Times by 20 take away 4. How to struggle at using a calculator by me. Minus 10 lots of, that would be 24, take away 20, take away 4. All over 16 cubed. So you get 7 over 128. There you go, got the answer eventually. 7 over 128. That, of course, is bigger than 0, so it's a minimum. If I can spell the word minimum. And then at t equals minus a third, d squared y over d, oh goodness me. Let's move that over, because apparently it doesn't like that. Do it all again, but with minus a third. So that will be, we'll have our minus 4 minus 10, which is minus 14, times by a very horrible number, so we are not going to manually work that one out. And then we're also going to plug in, we already know that's going to become 0. Why did I plug that in manually last time? I could have saved loads of time by just realizing that was going to become 0. And then, of course, plugging in that on the bottom as well. 10 over minus 3. Minus 4, all cubed. And you should get, in theory, minus 63 over 242, which is less than 0, which is therefore a maximum. There you go. So that is the nature of the two stationary points. T equals 2 is a minimum. T equals minus a third is a maximum, which is what we're expecting. If you remember what the graph was back earlier, we could see there was one minimum, one maximum. So that's very good news that we did get that confirmed. On to the third question. And I must admit, there's a part of me that's slightly already regretting this one. Finding the third order derivative. I put this one in just because I know some people might have been looking at the previous video and wondering what is the equation going to be for the third order derivative. So tell you what, let's find it. This one I'm going to prefer doing though in some ways because it's no plugging numbers in, because apparently that's the bit I struggle with. Joke. Right then, so we're going to of course have to do the quotient rule. Let's start with the top because we know that's going to be the bit that's the most painful part to do. So we're going to make u equal the entire top. I'm not going to split it up that much. You might choose to do that because we've got two product rules we're going to have to do as part of this, as well as implicit differentiation. Because remember, to find d cubed y over dx cubed, we're going to be differentiating with respect to x. That's the thing to bear in mind. Differentiate with respect to x, d squared y over dx squared. So if we're finding du over dx, that means we're going to have to differentiate all this with respect to x. So we're doing a product rule with that first pairing. So differentiate the d squared y over dt squared while keeping the other thing the same. So that will be a case of progressing the derivative, realizing that we have differentiating t's instead of x's. So we should correct that by doing implicit differentiation, and then timesing that by the other thing before it's been differentiated. Adding on our other thing differentiated while the d squared y over dt squared stays the same. So that would be d squared x over dt squared. But then again, the implicit differentiation correction. We differentiate t's, meant to differentiate x's, but we're not done. We're going to now take away the product rule for the other bit. So therefore, differentiating the dy over dt, doing the implicit differentiation correction, timesing it by the other thing before it's been differentiated. Oh, that was meant to be a squared, wasn't it, earlier? And then, okay, technically in brackets with an add. And then we have the dy dt not differentiated times by the d squared x over dt squared differentiated. But I'm going to differentiate the t's and then correct it using implicit differentiation. That is an interesting result because you might notice, of course, that there are going to be some things that cancel out. We've got d squared y over dt squared. Oh my goodness, missing out notation there. d squared x over dt squared, dt over dx being added and subtracted on the top. So that means you're going to be left with d cubed y over dt cubed, almost said it wrong, times by dx over dt. And then dt over dx, so remember for parametric equations, it's often helpful to realize that that could be written as dx over dt to the power of minus 1. I'm not going to cancel the dx over dt and the dx over dt to the power of minus 1 because, as you might have seen in the previous video, keeping this dx over dt to the power of minus 1 is helpful for creating a common denominator later, because with this other bit we got minus dy over dt times by d cubed x over dt cubed, and then times by, again, rewriting the dt over dx as dx over dt to the power of minus 1. Nice. So that's u differentiated. Wow. Differentiating v is actually going to be a lot easier. Still a bit of effort because we've got a bit of chain rule to do there, but not too bad, because that will be dv over dx being equal to, by chain rule, it's something cubed, so it's going to differentiate to 3 lots of that something squared, but then times by the derivative of the thing that's inside, which we'd want to say is d squared x over dt squared, progressing the derivative, but then we realize we differentiate t's, we're meant to differentiate x's. And again, therefore, that can be rewritten as well. So we could realize that this is 3 lots of dx over dt all squared times by d squared x over dt squared. And again, weirdly, although, well, I've got to rewrite the dt over dx, but might be tempting to, with the powers, cancel them out. I'm going to leave the power minus 1 though, because now when we try and find d cubed y over dx cubed, we are going to get our du over dx times by our v. So that is going to be, wow, okay, this is going to be pretty intense. We're going to have d cubed y over dt cubed dx dt all over dx over dt to the power of minus 1. I don't know why I said all over there. What I've written on the screen is correct. Times by the v, which is dx over dt all cubed. The other bit of the du dx, which was the minus dy over dt, d cubed x over dt cubed, times by dx over dt to the power minus 1, times by our v, which is dx over dt, all to the power 3. And that is the du over dx times by v bit done. Now we've got to do take away u times by dv over dx. And at this point, I'm realizing I'm already running out of room. My goodness, this question is, let's see, maybe I might be able to fit this in above my head. We'll see. Let's try and cram it in there. So we have u, which is all of that stuff, blimey, d squared y over dt squared dx dt minus dy over dt times by d squared x over dt squared, and all of that is times by our dv over dx, which was 3 lots of dx over dt all squared d squared x over dt squared, oh my goodness, times by dx over dt. Okay, we've run out of room. You can see what dv over dx is above. Basically, that's all going on the top. And then the bottom, we've got v behind there as dx over dt all cubed. But remember, on the bottom of question rule, it's v squared. So that would be dx over dt all to the power 6. Okay, we're not done though. We're going to simplify that a bit more. So, of course, the first thing you might notice is every single one of these terms now has a dx over dt to the power of minus 1 as a factor. That is why I didn't cancel that out at any point, even though in some places it could, because I can then, in the next stage, just move that dx over dt onto the denominator of the overall fraction to create an overall denominator of dx over dt to the power of 7. So that is what we're going to do as part of this. We've got that, and now I'm going to start to gather stuff together. So we've got d cubed y over dt cubed times by dx over dt to the power of 4. Wow. Power of 4. Nice. We are going to have, okay, this one's not going to simplify. We've got minus dy over dt times by, I've already forgotten it. Wow, that's how you know that there is too much stuff there. We have d cubed x over dt cubed. And we have a dx over dt all cubed. Cool. And then we also have all of those brackets to multiply out. So again, ignoring the dx over dt to the power minus 1, we've got a d squared y over dt squared. We've got a 3, so let's start off by writing that 3d squared, and it's a minus as well, pointing out, so minus 3d squared y over dt squared. We have a dx over dt all to the power of 3 in the end. You combine the two dx over dt expressions. And we also have the d squared x over dt squared. And then lastly, we've got the minus dy dt, but that's inside some brackets with another minus, so it's going to become plus. So that's a plus dy dt. Plus dy dt. Again, I've suddenly realized I missed out the fact it's being multiplied by 3. And we have dy over dt, d squared x over dt squared squared, and dx over dt squared. Wow, that is really crazy. So dx over dt squared, d squared x over dt squared, squared as well. Amazing. And we also then, as I said, we're done. We just need to have the denominator, which is all over dx over dt all to the power of 7. Oh my goodness.